We are going to solve for the eigenvalues, eigenvectors, and eigenspaces of this given 3 by 3 matrix. Here, we are already given with this characteristic equation that we were able to solve in the previous video. You might want to review on that as to how do we arrive at this form of characteristic equation. Here, we are going to use this in solving first for the eigenvalue represented by these lambda symbols. So here, we are going to make sure that this entire expression be equal to 0, and we can only be sure of that if 1, 2, or even 3 of these binomial expressions are equal to 0. In short, in solving for the lambda, for the first binomial expression, we are going to equate it to 0. In short, the first lambda, or the first eigenvalue of this 3 by 3 matrix is negative 5. The next value is when we are going to have lambda minus 7 equal to 0. In short, lambda, the second lambda is 7. And for the third one, you will have lambda minus 3 equal to 0. So the third lambda, or the third eigenvalue, is positive 3. Now, these are the three different eigenvalues of this 3 by 3 matrix. Again, this was made possible using the characteristic equation that we were able to solve in the previous video. Now, we are going to solve for the corresponding eigenvectors and eigenspaces of this 3 by 3 matrix using the different eigenvalues. To do that, let's try to review and go back to this notation. Lambda I minus A. Let us try to come up with a matrix form represented by this. But of course, here, the lambda will just stay as lambda. We will substitute the three different values of lambda later, as we will come up with a matrix form of this. I here is the identity matrix for a 3 by 3 matrix. So 1, 0, 0, 0, 1, 0, 0, 0, and 1. So add it here. We have 1, 0, 0, 0, 1, 0, 0, 0, and then 1. Minus our A here is negative 5, 0, 0, 3, 7, 0, 4, negative 2, and then 3. Next is simply multiply first the lambda. So you will have here lambda 0, 0, 0, lambda 0, 0, 0, lambda, minus this entries negative 5, 0, 0, 3, 0, 7, 0 rather, 4, negative 2, and 3. Since both matrices are 3 by 3 matrices, in short, the difference is defined, and we will have this final form. We have lambda minus negative 5, so lambda plus 5. 0 minus 0 is 0. 0 minus 0 is also 0. Next, 0 minus 3 is negative 3. We have lambda minus 7. 0 minus 0 is 0. Then 0 minus 4 is negative 4. We have 0 minus negative 2 is positive 2. And we have lambda minus 3. This matrix now will then be used when we are going to solve for the eigenvectors of the specific eigenvalues here. We are going to come up with, again, this expression here, lambda I minus A, and multiply this with a certain vector x and equate it to the 0 vector. This will correspond to the eigenvector or eigenvector of the specific eigenvalue. And of course, since we are on a 3 by 3 matrix, this is an element of R3, so x sub 1, x sub 2, and x sub 3. In short, we're going to solve for x sub 1, x sub 2, and x sub 3, and to complete the eigenvector. Of course, the 0 matrix of R3 is 0, 0, 0. So let's start with the first eigenvalue. When substituting negative 5 to the lambdas here, this would be the equivalent matrix. You have negative 5 plus 5, 0, 0, 0. Negative 3, negative 5 minus 7 is negative 12, 0. We have negative 4, you have here 2, negative 5 minus 3 is negative 8. Alright. this will be multiplied with this vector x sub 1, x sub 2, and x sub 3. Okay? To be equal to 0, 0, and 0. There are a lot of processes that will allow us to solve for x sub 1, x sub 2, and x sub 3 values here. But one thing that is also applicable is if we're going to come up with the reduced row echelon form of this. By the way, in the previous video, concerning the same process, we're able to just automatically analyze the connections of the terms. But since we don't have specific values here, so let's simply come up with a reduced row echelon form. Let us try to interchange row 1 and row 2. So you will have this form. Row 1 will become row 3. So we're going to place the zeros, or the row of zeros, at the bottom portion. And I will have row 2 to become the new row 1. And we'll also have row 3 to become the new row 2. In short, we'll have negative 3, negative 12, 0. We will have here negative 4 to negative 8. And of course, all zeros here. Then we are going to multiply negative 1/3 to row 1, so that we will have a leading 1. So let me use the spaces here at the bottom. So we have 1 here. Negative 12 times negative 1/3 will become a positive 4, 0. This is still negative 4 to negative 8, 0, 0, and 0. Then we're going to make this 0 by multiplying 4 to row 1, plus you're going to have row 2. Okay? For a new row 2. So we will have 1, 4, 0. This is now 0. 4 times 4 here is 16, plus 2, you will have 18. You will have 4 times 0 is 0, so you have negative 8 here as well. Alright. So finally, let's make this 1 by multiplying 1 over 18 on row 2 for a new row 2. So we could come up with our reduced row echelon form. We have 1, 4, 0, 0. We have 1. So negative 8 over 18. In lowest terms, you have negative 4/9. Please kindly check if it's correct. Divide by 2, divide by 3, yes. And we have 0, 0, and 0 here as well. Now this is a row echelon rather, not the reduced row echelon. This is the row echelon form. After this, we can say that when multiplying with the vectors x sub 1, x sub 2, x sub 3, or the vector with entries x sub 1, x sub 2, x sub 3, you have x sub 1 plus 4x sub 2 equal to 0. And you will have here x sub 2 minus 4/9 x sub 3 is also equal to 0. When you look at here earlier, you were able to reach a row of zeros here. And if we're going to multiply this x sub 3, that would mean we're going to let x sub 3 here as an arbitrary variable or constant t. In short, after this, your second equation will be x sub 2 minus 4/9 t equal to 0. So you have x sub 2 is positive 4/9 of t. This is your x sub 2. And for this here, you will have x sub 1 plus 4 times 4/9 of x sub 2 equal to 0. No longer x sub 2. My bad. T is equal to 0. So if x sub 1 plus 16 over 9, t equal to 0. So x sub 1 is negative 16/9 of t. In short, the eigenvector when our eigenvalue is, what the value eigenvalue here? Negative 5. Okay. Negative 5 is equal to this notation. You have negative 16/9 t, 4/9 of t, and you have here your t. Okay. Let's make this better. Like that. When you factor out t, you will have here negative 16/9, 4/9, and you have 1. Okay? And then your Eigenspace is a set containing t times negative 16 nines, 4 nines, and 1, such that t is an element of R, but not an element of the set containing 0. This is your eigenspace, eigenvector for the specific eigenvalue. Now let's do the same thing. I hope that I still have a lot of space here, but let's just hope that we can fit all results here. So we'll have the second eigenvalue, which is positive 7. Substituting that here, you will have this matrix. 7 plus 5, that's 12, 0, 0. Negative 3, 0, 0. You have negative 4, 2, and then 4 here. So this is equal to, or if we're going to multiply this with your x sub 1, x sub 2, and x sub 3, and equate it to 0, 0, 0. So how do we solve this? So we are going to look at the results here, and then we are going to come up with some analysis. You can see here that if you're going to multiply this first row with this entries of the vector, you will get here x sub 1 or 12x sub 1 equal to 0, because that's 0, x sub 2, and x sub 3. In short, x sub 1 is 0. This is already the value of your first entry of your eigenvector. This is also true even if you're going to use this one. You will have negative 3x sub 1 equal to 0, which will still give us x sub 1 equal to 0. Hence, we will have this last row. You will have negative 4x sub 1 plus 2x sub 2 plus 4x sub 3 equal to 0. But of course, again, x sub 1 is 0, so you will have 2x sub 2 plus 4x sub 3 just equal to 0. There are two variables now. So again, we will let x sub 3 be an arbitrary constant s. In short, 2x sub 2 plus 4s equal to 0. You will have 2x sub 2 is equal to negative 4s. And then your x sub 2 is equal to negative 2 of s. Okay? So this would mean that your eigenvector here for your eigenvalue, which is 7, is the vector. You will have 0 for x sub 1, x sub 2 is negative 2s, and your x sub 3 is s. When you factor out s, you will have 0, negative 2, and 1 here. This is your eigenvector now. And to generalize the entire possible values, you will have your eigenspace here, set of s times 0, negative 2, 1, such that s is an element of R, but an element of the 0 vector. So let's have the last one. Yeah, I still have a lot of space here. Hopefully this is enough. The last eigenvalue is 3, right? We're still going to use this here. So hopefully we could, it's not enough. So we'll have to rewrite that. Our third eigenvalue is 3, and our form here is this. Pardon with me. You will have lambda plus 5. Okay, you will have 0, 0. That's lambda again plus 5, 5. 0, 0. Negative 3, lambda minus 7, 0. Okay. Minus 7, 0. Negative 4, 2, and lambda minus 3. Let us check. Negative 4, 2, and then lambda minus 3. Okay. Substituting 3, you will have here this matrix. You will have 8, 0, 0. Negative 3. You have negative 4, 0. Negative 4. Okay. Negative 4, you will have 2, and then 0 here. So if you're going to multiply this with x sub 1, x sub 2, and x sub 3, and equating this to 0, 0, 0, same thing as earlier. Multiplying this first row, you will have 0, or I mean 8 x sub 1 equal to 0, which means your x sub 1 is just equal to 0. The next here is we are going to use the second row here. So you have negative 3x sub 1 minus 4x sub 2 equal to 0. We know that x sub 1 is already 0. So you have minus 4x sub 2 equal to 0. X sub 2 is also 0. And to finalize our x sub 3 here, we'll have the third equation. So negative 4x sub 1 plus 2x sub 2 equal to 0. These are both zeros, but x sub 3 did not occur here. This would mean, looking at the third column, 0, 0, 0, if we're going to multiply this with all the entries, s sub 3 will, or this will become 0 now. So simply assign another arbitrary constant for x sub 3, because it will always be true for all values of x sub 3, which is w. This would mean your eigenvector here is, you have 0, 0, w. Factoring w, you have 0, 0, and, sorry for this, 0, 0, and 1. So our eigenspace here is set of w times 0, 0, 1, such that w is an element of R, but not an element of the set containing 0. So eigenspace, eigenvector of the eigenvalue, which is a 3, and the same goes on. This is how, again, we verify or we solve for eigenvalues, eigenvectors, eigenspace of the 3x3 matrix using an already identified characteristic equation. Thank you very much for watching.